We're going to look at the difference between a gradient field and an irrotational field, and also something called the curl test for identifying when an irrotational field is a gradient field. A common example vector field for looking at this is f equals negative y over x squared plus y squared I plus x over x squared plus y squared j. This vector field is sometimes written as negative yi plus xj over x squared plus y squared. What does this vector field look like? Say we're at a point x, y, then it has position vector r equals xi plus yj connecting from the origin to that point. Why did I write the position vector? Because if we look at the gradient field and think about its direction related to this position vector, this is the rare case where the direction of the position vector helps us figure something out. Take the dot product between f and r. It's 1 over x squared plus y squared, negative yi plus xj, dotted xi plus yj. So this x hits this negative y, and this x hits this y. You can see this dot product is 0. And so it turns out this vector field is always perpendicular to the position vector to a point. In addition, the length of these vectors is getting shorter as we get further and further from the origin. Looking at this vector field, we can ask the question, is it circulation free? And I think it should be sort of visibly clear that it's possible to construct a path on which there is circulation. I'll just draw in the unit circle. And if we traverse it counterclockwise, we see that the vector field is aligned with it at every single point. So clearly there's circulation along this path. This vector field is not circulation free, so we are not going to call it a gradient field. I'd said this was an example of an irrotational vector field, so let's compute the scalar curl for this vector field. So we write the vector field component-wise. F1 is this first component times I plus F2 this second component times j, and the scalar curl is the partial of F2 with respect to x minus the partial of F1 with respect to y. We think of this scalar curl in terms of the vector field pushing on a pinwheel. So the F2 component of the vector pushes on these arms of the pinwheel, and we care about how the length of those vectors is changing with respect to x. So that's this term, and when the length is increasing with respect to x, they're pushing on our pinwheel in a counterclockwise direction. And then we also care about how the x components, that's F1, the I direction piece, changes as we change in y. And if they're getting longer, they're actually pushing in the clockwise direction. That's the negative direction. So if we subtract, we take the counterclockwise push and we subtract the clockwise push, we get the net counterclockwise push. That's our scalar curl. Now let's compute it. We have F1 equal to negative y over x squared plus y squared, and F2 equal to x over x squared plus y squared. To compute the partial of F2 with respect to x, we can use the product rule, so we need to rewrite F2 slightly to use the product rule. Rewriting F2 as a product of x and x squared plus y squared to the negative 1, we're ready to take the derivative. And so for the first piece, the derivative of x is 1, and we keep this term, so we have x squared plus y squared to the negative 1. And for the second part, we keep this and take the derivative of this, and so we have plus x times negative 1 times x squared plus y squared to the negative 2, and then with the chain rule, times 2x. Similarly, for the partial of f1 with respect to y, we have negative x squared plus y squared to the negative 1 minus y, negative 1 times x squared plus y squared to the negative 2, and then with the chain rule, we have a 2y. Putting these two terms together to find the scalar curl, we take the partial of f2 with respect to x, and we subtract the partial of f1 with respect to y. And so we have 1 over x squared plus y squared minus 2x squared over x squared plus y squared, the quantity squared, minus negative 1 over x squared plus y squared plus 2y squared over x squared plus y squared, the quantity squared. And this is equal to, okay, let's see, this term and this term, that those two minuses can combine to a plus sign, so this is actually 2 over x squared plus y squared. And the other two terms both have a factor of 1 over x squared plus y squared squared. 1 over x squared plus y squared squared times negative 2x squared minus 2y squared. Factoring out the negative 2, we have 2 over x squared plus y squared plus negative 2 times x squared plus y squared over x squared plus y squared. This cancels there, and so we have 2 over x squared plus y squared minus 2 over x squared plus y squared. This is equal to 0, and so our vector field is irrotational everywhere that it is defined. Going back to our vector field, this is a bit surprising. It means that if I put a pinwheel in, it's not going to turn. And that's a little bit surprising because we can see that the vector field does sort of have some kind of net rotation. We can tell it has circulation. So why is it irrotational? Well, it's irrotational because this vector field is actually moving as a block. And so if we put a tiny little pinwheel in, it is just going to get shifted with the vector field. So the vector field will just shift it all around without actually spinning it. That's what the result tells us that our scalar curl is 0. Of course, there's one place where if we were to put in a pinwheel, we would get rotation. And that is the spot where the vector field is undefined. So that vector field is undefined at the origin because of this over x squared plus y squared. And if we put in a pinwheel right at the origin, actually the push on its arms would cause it to spin in a positive direction, but we can't put a pinwheel there. The vector field is not defined right at the origin. Let's compute the line integral about the unit circle. Note that we can't use Green's theorem. It seems like we should be able to because the scalar curl is 0 everywhere that we computed it, but the vector field is not defined at the origin. And because the vector field is not defined at the origin, when we look at this region enclosed by this curve, the vector field is not defined everywhere. And so because we have this hole in the domain of the function of the vector field at the origin, we can't use the theorem. This whole region isn't there to integrate around. If we were to choose any other region, any other closed curve that doesn't enclose the origin, okay, no problem. Everywhere inside this closed curve, the vector field is defined and the scalar curl is 0. So on every single one of these curves, our vector field is circulation free. It's just this one family of curves that encircle the origin, however strangely they might encircle the origin. If they encircle the origin, then we can't use our theorem and we're going to have to calculate the line integral directly. Okay, so here's the vector field. I parameterize the unit circle, cosine t I plus sine t j, 0 to 2 pi in t. And now I'm going to plug in to find f of r of t. And I find negative sine t divided by sine squared plus cosine squared. That's just 1, so negative sine t I plus cosine t divided by sine squared plus cosine squared. So that's 1 as well, so cosine t j. And then I'm going to find dr dt, because ultimately I'm going to be integrating f dot dr dt, integrated with respect to time. Dr dt is negative sine t, the derivative of cosine I, plus cosine t, the derivative of sine j. Taking the dot product, I have sine squared t plus cosine squared t. So this dot product is 1. Setting up my line integral, my bounds in time were 0 to 2 pi to go around the unit circle, and f dot dr dt will be integrated with respect to time, but this was just 1. So this will be the integral from 0 to 2 pi of 1 dt, which is equal to 2 pi. So in that vector field, the circulation about the unit circle was 2 pi. And so that means, yes, we're correct that these vectors were aligned with the unit circle, and specifically they were pushing along it, and the amount that they were pushing integrates to 2 pi. What can we generalize from this example? Our vector field wasn't circulation free because although when lines didn't encircle the origin, we were able to use Green's theorem, and since it's irrotational, when we can use Green's theorem, of course the circulation is 0 around a path, there was a set of curves where the curve is completely within the domain of the vector field, no problem, but the region that the curve enclosed was not completely in the domain of the vector field. And so that's what caused a problem here. So if a curve C, which is the boundary of a region R, is in the domain of F, and R is in the domain of F, then the scalar curl being 0 on R tells us that the circulation is 0. And so the problem is for vector fields where this doesn't hold everywhere. Vector fields where we're able to draw a curve that lies within the vector field, but which encloses a region where there's some point where the vector field's undefined. That's where the problem is. And so that leads to something that's called the curl test. If for every closed curve, that lies within the domain, we can sort of look at these. They don't have a whole. You could imagine shrinking these curves, and you can shrink them all the way to a point. So shrink the curve, and it stays within the vector field the whole time you shrink it. But if you shrink this one, you can see that as you shrink it, it encloses this bad point, and so it can't just shrink away to nothing. And so that's how people often think about this curl test. Is there any closed curve in the vector field that you can't shrink away while keeping it within the vector field? Okay, well, if there is, we've failed the curl test, and we can't use Green's theorem to show that our irrotational field is a vector field, is a circulation-free field, is a path-independent field.